Hello viewers, welcome to this next session on stereochemistry of organic compounds. Today's session has been planned in a way that first we will take up what we had discussed in our previous session, then we shall discuss about the EZ configurational nomenclature of geometrical isomers. This will be followed by the rules which are used for assigning priorities to various groups for assignment of this EZ configuration to geometrical isomers. Then we will move on to the two-dimensional representation of our three-dimensional organic molecules, and finally we will summarize our today's work. In previous session we discussed that isomerism consists of two types, stereoisomerism and structural isomerism. Stereoisomerism itself is of two types, configurational and conformational, and amongst the configurational isomers we discussed about the geometrical isomers. We discussed that there are two basic requirements for a molecule to show geometrical isomerism. One is that there should be restricted rotation, and second, the two atoms under consideration should have two different groups attached to them. Then we discussed that these isomers are assigned the configuration as cis and trans on the basis of the substituents which are present on them. If the identical groups are present on the same side, the isomers are called cis, and if they are in the opposite direction, then they are called trans. But the problem came for the nomenclature of compounds like 1-bromo, 1-chloropropene. In such compounds there is no common group. How to assign a configuration to such compounds? Then a new system was given which is called as EZ nomenclature. This system was given by three scientists, R.S. Kahn, Sir Christopher Ingold, Vladimir Prelog. This system is also known as Kahn, Ingold, Prelog or CIP system for configurational nomenclature. In this system there are two steps. The first step is that the two groups on each of the carbon under consideration for geometrical isomerism are assigned certain priorities, and these priorities are based on certain rules which are called sequence rules. And then second step is that we see now the groups of higher priorities. If the groups getting the same priorities are on the opposite side, then that isomer is assigned as E configuration, and if the group getting the same priorities are on the same side, then this isomer is assigned as Z configuration. This E and Z are derived from two German words, entgegen and zusammen. Entgegen means opposite and zusammen means together. So in this system the two different geometrical isomers are assigned as E or Z. Now let us discuss the rules. The first rule for assigning the priorities to groups is that we look at the atoms which are attached to alkene carbon, and the atom with higher atomic number gets the higher priority. That is, we call it as precedes over the atom with lower atomic number. Such as this is a sequence of groups given: iodine precedes bromine, bromine precedes chlorine, chlorine precedes sulfur, then fluorine, oxygen, nitrogen, carbon, hydrogen, and the least priority is given to the lone pair of electron if it is present at any position. So this is the sequence in which these groups are assigned the priorities, and the group which comes before, that is whose atomic number is more, we call it as getting the higher priority, or sometimes we also call it as first priority, and the other group gets the lower priority or the second priority. Then if there are two atoms which are isotopes of each other, then the heavier isotope gets the higher priority. For example, if there are deuterium and hydrogen at any place, then deuterium is given the higher priority. Similarly, if there are two different isotopes of carbon present, say C13 and C12, then higher priority will be assigned to C13. Let us take some example. Now, we had earlier the problem with the compounds where there is no common group, such as 1-bromo, 1-chloro-propene. Now, here are the two different geometrical isomers. We assign the priorities to the groups according to the rule that we have just studied. Out of this methyl and hydrogen which are present to one carbon, methyl is attached through carbon. So, methyl gets the higher priority over hydrogen, means hydrogen gets the lower priority. On the other side, we have two atoms attached, one is chlorine and one is bromine. The atomic number of bromine is more, so bromine gets the higher priority. So, what we find in this particular configuration, that the two groups getting the higher priority are on the same side. So, this isomer is assigned the Z configuration. Similarly, the other isomer, we find that the groups getting the higher priorities are across, they are in the opposite directions. So, this isomer is assigned as the E configuration. Let us take another example. Say we have 1-bromo, 1-chloro, 2-fluoroethene. There are 3 halogens. What we see that on this side fluorine gets a higher priority over hydrogen, whereas on this side bromine gets the higher priority over chlorine. So, the groups getting the higher priorities are across, they are opposite. So, this isomer is again assigned the configuration E. So, it is named as E 1-bromo, 1-chloro, 2-fluoroethene. Let us have another example. This is 3-chloro-2-pentene. In this case, again the two isomers are here, and we see that methyl gets the higher priority over hydrogen, because methyl group is attached to carbon and atomic number of carbon is more than that of hydrogen. On this side there is chlorine and ethyl group. The atomic number of chlorine is more than that of carbon. So, obviously chlorine gets the higher priority. So, in this particular isomer again we find the groups getting the higher priority are across. So, it is assigned E configuration, whereas the other isomer, the groups getting the higher priority, that is methyl and chlorine, they are on the same side. So, this isomer is assigned the Z configuration. Let us take the example of 1,4-dimethyl cyclohexane that we have discussed in our previous session. This is one isomer for this when the two methyl groups are on the same side, and the other isomer is when the two methyl groups are across. This is cis 1,4-dimethyl cyclohexane, and this isomer is assigned the trans configuration. It is called trans 1,4-dimethyl cyclohexane. Now, according to EZ system, the methyl group gets the higher priority over hydrogen, and two groups getting the higher priority are on the same side. So, this isomer is assigned Z configuration, whereas in this case the two methyl groups which are getting the higher priorities are across. So, this isomer is assigned E configuration. We can use this EZ nomenclature for assigning the configuration in case of aldoxymes also, that we had studied in our previous session, where we used syn and anti for their configuration. In aldoxymes, one of the position on nitrogen is occupied by lone pair of electron, and we have seen earlier that lone pair of electron is assigned the lowest priority. Out of these alkyl group and hydrogen, now hydrogen gets the lower priority and this alkyl group gets the higher priority. Obviously, alkyl group is attached through carbon, whereas on nitrogen one group is hydroxyl group which is attached through oxygen, and this group gets a higher priority over the lone pair of electrons. So, what we find that the two groups getting higher priority are across. So, this isomer is assigned the E configuration. Obviously, the other isomer which will have hydroxyl on this side will be assigned Z configuration. We can take the example from azo compounds also. In azo compounds, each of the nitrogen has got one pair of electron and one phenyl group here. The phenyl group obviously gets the higher priority over the lone pair of electron, and the groups getting the higher priority are across. So, this particular isomer is also assigned E configuration. Now, the problem comes with the compounds like this, which is 3-methyl 2-pentene. Here when we try to assign the priorities to groups, we can assign higher priority to methyl group over hydrogen because this is attached through carbon. But on this side the one group is methyl, other group is ethyl, and both are attached through carbon. Now which group should be given the higher priority? Our first rule for assigning the priority cannot be used here. So another rule was given, and that second rule is that if two substituent atoms are same, then the next atom away from the double bond is considered along the chain until a difference is found. Means if we look for the second atom, and if priority cannot be decided by the second atom, then we go for third atom in the chain of the substituent. Precedence is decided at the first point of difference, means wherever we find or we meet an atom of higher atomic number in any group, then that group will be assigned the higher priority. Let us take an example. Say ethyl group and methyl group. Now what happens? In ethyl group, the first atom carbon is now attached to 2 hydrogens and 1 carbon, whereas in methyl this carbon is attached to all the 3 hydrogen atoms. So we find a difference here. We find that 1 carbon is there in place of 1 hydrogen. So obviously this group is assigned the higher priority because we are meeting a atom of higher atomic number at the second place. So in our previous example, this group will be given higher priority. Similarly, the priorities can be used for other groups, like if it is CH2Br, it is given higher priority over CH2NH2 because atomic number of bromine is more than that of nitrogen. This is given higher priority over ethyl group because this carbon has a lower atomic number than this nitrogen, and so on. So the example that we were doing, that methyl is given the higher priority over hydrogen, and now ethyl is given the higher priority over methyl. So what we find, the two groups getting the higher priority are across. So this particular isomer is assigned the E configuration. Now we can take some more groups. Let us talk about isopropyl group and then CH2CH2OH group. Which of these two group will precede or will get the higher priority? When we break up this, we find that in this case the first carbon has got 1 hydrogen and then 2 more carbons attached to it because there are 2 methyls. So second level atoms are carbon, carbon and hydrogen. Whereas in this case CH2CH2OH, although it has one hydroxyl group, but we have to look for the atoms at the second position, and we find that after this carbon we find there are 2 hydrogens and 1 carbon. So we meet 1 carbon here in place of 1 hydrogen. Carbon has higher atomic number, so this isopropyl group is given the higher priority over CH2CH2OH group. Let us take another example. If it is even tertiary butyl group, and here it is simple CH2OH group. Here we find that CH2OH group precedes over this tertiary butyl group. The reason being that at the second level in this we find that there is 1 oxygen and 2 hydrogen, whereas in this molecule at the second level all 3 are carbon atoms. So although there are 2 hydrogens, but we meet 1 atom of higher atomic number, that is oxygen. So that is why CH2OH group is given the higher priority over tertiary butyl group. Let us take one more type of example. In this case again, on this side priorities can be decided. One is hydrogen, other is methyl, which is attached to carbon. There is no problem in this. On this side we find it is one aldehyde group, C double bond OH, and then one CH2OH. So we find that first atom in both the cases carbon, second atom in both the cases hydrogen and oxygen, here also hydrogen and oxygen. But for the groups which are joined by double bond or triple bond, then there is another rule for deciding their priorities. Where there is a double or triple bond, both atoms are considered to be duplicated or triplicated. Means CO group is equivalent to 1 carbon, 1 oxygen, right. Now these are attached by double bond, So, both these atoms are duplicated, means it is considered as if this carbon is attached to one more oxygen, which is this, and this oxygen is attached to one more carbon, which is shown like this. These atoms are called host atoms because they actually do not exist. These are fictitious atoms which we are considering for assignment of priorities to different groups. And now we use this rule for assigning the priorities to example which I have taken earlier. The CHO, it is considered as equivalent to now COOH, whereas CH2OH is COHH. Obviously, in this case we are having two oxygens, so this group gets the higher priority over this group. And we assign the configuration of this molecule that methyl gets the higher priority over hydrogen, whereas this aldehyde group gets the higher priority over CH2OH. Since the two groups getting the higher priorities are on the same side, so this isomer is assigned as the Z configuration. Now, there are certain misconceptions. The most common misconception among the mind of the student comes that cis and trans and Z and E have some relationship. That cis we were deciding the groups on the same side, similarly we are saying Z on the same side, but they do not have any relation. Please keep it in your mind because they are based on fundamentally different naming rules. In cis and trans nomenclature method, we are considering the groups which are identical, whereas here we are considering the group with their priorities. Let us take an example. This molecule is 2-bromo-2-butene. Is this cis or trans? Obviously, this is cis because it has two methyl groups on the same side. Now, we try to assign configuration according to EZ system. In this case, what we find, methyl gets the higher priority over hydrogen on this side, whereas bromine gets the higher priority over methyl on this side. So, groups getting the higher priority are across, right. So, this isomer is assigned E on configuration. So, cis and trans and E and Z, they are not related, they are independent methods, so should not be compared. Now, if we have to assign the configuration to compounds which contain more than one double bonds in them, like this molecule, then the method is that each double bond is assigned the configuration, and then before the name the configurations are written with the position of these double bonds. Let us look at this molecule. Across this carbon-carbon double bond, the two groups are on this side, chlorine and hydrogen, and chlorine gets the higher priority. And on this side, one hydrogen and one next is CH2 group. So, obviously, CH2 group is a higher priority. So, this higher priority group and this is a higher priority group, they are across the double bond. So, configuration across this double bond is E. Now, let us look across this double bond. There is one methyl, one chlorine. Obviously, chlorine gets the higher priority. Across this, we have hydrogen and then again a CH2 group. So, this CH2 group gets the higher priority. So, the two groups getting the higher priority, CH2 here and chlorine here, are on the same side. So, the configuration across this double bond is Z. So, then we will write the correct name for this compound as 1E4Z, because in IUPAC system this will be carbon number 1. This compound is 1,5-dichloro and 1,4-hexadiene. So, across 1 and 2 carbon double bond which begins at 1, we write the configuration here as 1E. This double bond which begins from carbon number 4 and is between carbon number 4 and 5. So, we assign the configuration for number 4. So, it is 1E4Z 1,5-dichloro 1,4-hexadiene. So, this is about the nomenclature for configuration of geometrical isomers. Now, in the next part, let us discuss that how do we draw our 3-dimensional molecules on our notebooks, on the blackboard or in the books, because all these are two dimensional, whereas our organic molecules are three dimensional. Whenever we represent a three dimensional object into two dimension, we call it as projection, and different type of formulae we use for writing the molecules in two dimension, which are called projection formulae. The different projection formulae which are used are Wedge-dash projection, Fischer projection, Newman projection, and Sawhorse projection. Each of these formula is drawn and then visualized with certain specific rules. Let us take these projection formulae one by one and understand them with the help of models. The first is wedge-dash projection. In wedge-dash projection, the molecule is viewed in such a way that two of its substituents or two of these bonds are considered in the plane of paper. Say this is the plane of paper. Then one group is going inside the plane of the paper and one is coming out towards the viewer. I have this model in my hand, and let us compare it as it is shown there on the screen. We find that this is carbon. It is attached to white group and red group, which are in the plane. These are drawn with thin lines. This white group and red are drawn with thin lines. The group which is coming towards the viewer, that is coming out of the plane of the paper, is shown as a dash, and this wedge is here. This is the blue group which is shown on this wedge. And then the group which is going inside the plane, going away from the viewer, is shown with the help of these dotted lines, a dotted wedge. This is the green group shown here. So this is called wedge and dash projection. We can view the molecule in any way. It is not necessary that I am holding the molecule only this way it can be drawn. It can be drawn like this, that we take this white and blue group in the plane, then green is going inside, red is coming out. We can hold it like this, that red and blue are in the plane of the paper, and then white is going inside, green is coming out. So whatsoever way we want to view, we can draw the molecule in the same way. This is called wedge and dash projection. Then next is Fischer projection. In Fischer projection, again, molecule is considered as if it consists of two intersecting planes. That is, two of the groups are considered on one plane and two of the groups are considered on another plane. This is one plane and this is another plane, which are perpendicular to each other. And molecule is viewed from such a direction so that the horizontal plane has the groups which are coming towards the viewer, and the vertical plane has the groups which are going away from the viewer. Like as I am holding this molecule in my hand and I am viewing from this direction, on my right is a white group, on my left is a blue group, on top going behind is the red group, and going down is the green group. See here on the screen that this is a viewer viewing into a molecule where the groups are shown as A, B, C, D. This is a horizontal plane which has C and D groups which are projecting towards the viewer, and A and B are the groups which are in vertical plane going away from the viewer. So what that viewer will visualize? The viewer will visualize that group C is on the left side, group D is on the right side, A is on the top, B is downward and on the vertical plane. Then Fischer projection is drawn as a cross. We don't put carbon in between. It is understood that there is carbon here, and we write only the groups on the cross. So this A and B are on the top and bottom, whereas C is on the left and D is on the right. This is the right projection as the viewer was viewing this molecule. But again, we can have different type of Fischer projections because we can view the molecule from this side or from this side, but they will definitely represent the same molecule. Let us understand it in a different way also. This is a molecule and viewer is viewing from this side. and these are the two groups, pink group and yellow group. They are projecting outward in the horizontal plane, whereas this green and blue groups are going away from the viewer in the vertical plane. The viewer observes it like this, that carbon has this pink group on the left, yellow group on the right, green group on the top and blue group on the bottom. And we draw Fischer projection for this in this way. We draw a cross. Here is a carbon, on the right side is yellow group, on the left side is pink group, on the top is green group, and here is blue group. Remember that once drawn Fischer projection, we cannot give it a rotation of 90 degree or change the position of group. There are certain rules for this also that we will discuss later while discussing optical isomerism in our next session. Then another projection is called Newman projection. Newman projection is generally used where we have to consider two carbons simultaneously, and in this case we view the molecule along the carbon-carbon axis in such a way so that the first carbon is visible to the viewer, whereas it is obscuring the carbon behind it. And when we draw it, it is drawn like this, that front carbon is drawn as a point and the three groups coming from it are shown as three lines with exactly angle of 120 degree. Actually 120 degree I am saying because this is in one plane. Actually this angle is 109.4 degrees. Similarly, the back atom is shown as a circle and then three groups attached to it are shown from the periphery of the circle. And if we combine the two, we get this type of pictures. This B and F are just representing, B represents the group on the back atom and F represents the group on the front atom. It is shown again with the help of another model which is in Wedge-dash model. Viewer is viewing from this side. So this is the front carbon and this becomes the back carbon. This is shown with the blue color, this is shown with the red color. So this groups on the front carbon are shown like this. It's a dot representing the front carbon and these are the hydrogens of the front carbon. Whereas this is the second carbon which is shown with a circle and the groups attached to it are shown from the periphery. This Newman projection is very helpful in understanding the conformations of different molecules. Again, we will discuss it in our future episode. Then we have a Sawhorse projection. Sawhorse projection views the molecule in such a way so that a relative position of all the atoms or groups are visible. It is like as we can see the four legs of an animal when standing like this, and two substances become like this, and it is drawn like this. This axis represents a carbon-carbon axis, and then these are the three groups attached to the front carbon and these are the three groups attached to the back carbon. Again we can show rotation about carbon-carbon single bond, the position for the group may change, and this conformation is also very much helpful in understanding the conformations for molecules. So in our today's session we reviewed the work of our previous session, then we discussed that how we can assign E and Z configuration to different geometrical isomers. We also studied the rules for assigning the priorities to various groups, and then we discussed that how three-dimensional organic molecules are represented in two dimensions. In our next session we shall discuss about